Okay, good morning, everyone. A little bit of orientation, as always. Assignment 4 due for the undergrads tonight, and assignments 7 and 8 due for the grads tonight. And then tomorrow, next week on Tuesday, assignment 5 for the undergrads, and the graduate students will be finishing up the first 10 assignments, 9 and 10. Next Tuesday, I will talk briefly about what the grad students can expect when they recapitulate all 10 assignments, but this time not in PyBullet, but in a differentiable simulator. Talk about that next week. Any questions about the assignments? So far, so good? Marching on? Okay. All right, so back to lecture material. We're working our way through the admittedly brief history of evolutionary robotics. And we ended last time when we concluded lecture 7 by looking at a particular evolved neural network, and I made a big deal of that neural network right at the end of class, and I went a little quickly because I wanted to finish, so let me reinforce the message of that evolved neural network. It was inside the gantry robot that was evolving an ability to distinguish between triangles and rectangles, and specifically to run away from rectangles and approach triangles. What that evolved neural network did not have inside was a triangle recognition module and a rectangle recognition module, where in the triangle recognition module, it looks for black shapes that have 3 sides, and in the rectangle module, it looks for dark shapes that have 4 sides. If I were to ask you to describe a triangle and a rectangle, that's probably how you would describe it. Obviously, that's what a triangle is. It's something that has 3 sides, rectangle has 4 sides. It's obvious. The evolved neural network, if it was able to speak, would not describe a triangle in that way. The gantry robot with that evolved neural network inside would say something like, a triangle is something that when I sweep my 2 fovea, my 2 visual points of focus, when I sweep those 2 fovea to the left, one of them turns dark, and a certain period of time later, the other one turns dark. That's what a triangle is. If we were to ask it what a rectangle is, it would say something very similar, except it would say when the first fovea goes dark, it takes a little bit less time or a little bit more time for the next fovea to go dark. That hypothetical verbal description from the gantry robot involves movement. It turns or it moves. It involves vision, the fovea. It involves timing. This goes dark, then this goes dark. And because it's about timing, it also involves memory. Somehow that evolved neural network has to have recurrent connections and be able to maintain a little bit of internal state, which is its indirect way of remembering, quote unquote, when the first fovea went dark, and so on. That's, in a nutshell, the embodied cognition approach to creating intelligent and safe machines. We should provide enough breathing room for the optimization process, in this case an evolutionary algorithm, to find whatever solution reliably works for the machine, in that case the gantry robot. And one of the things that's challenging and exciting, in my opinion, about evolutionary robotics in particular, is it often stumbles on very non-intuitive descriptions or solutions, yet pretty robust and pretty reliable. Okay. Also, finally, yet another reminder that thinking about thinking is misleading. If I were to ask you what a triangle is, and you give me an explanation that has to do with 3 sides and 3 angles, you also have fovea. Your eyes also saccade, meaning they jump around. It's possible that your real understanding of triangles is actually much closer to the gantry robot's understanding of triangles. You just don't know it. It's subconscious. Consciously, if you're asked to self-report, describe something about your own thinking or your understanding of the world, it's possible, or seems increasingly likely, that in some cases we give an answer that's not actually what's going on under the hood. Okay. Today, we're going to move on to lecture 8. We're going to look at a particular type of neural networks that tends to be used in evolutionary robotics, for reasons we'll see today. And if we finish up lecture 8, we might move into lecture 9, the minimal cognition experiments. In the minimal cognition experiments, the experimenters tried to strip away complexity of the body, complexity of the brain, complexity of the environment. as you'll see in the minimal cognition experiments, they have very, very simple robots and simple environments, and they're trying to focus on evolving those simple robots to exhibit the building blocks of intelligence. If you agree with Turing that intelligence is impossible to define, but we know it when we see it, let's try and make machines that exhibit more and more aspects of intelligence so that they start to pass the physical Turing test. And in the minimal cognition experiments, we're going to see them tackle 4 features or 4 behaviors that most intelligent organisms and machines probably should have. Okay, but before we get there, let's talk about CTRNNs. What are CTRNNs? It's a bit of a mouthful. It stands for continuous time recurrent neural networks. So neural networks, you know, remember our discussion about neural networks. Recurrent, hopefully, should also be familiar to you. There's going to be some recurrent connections in CTRNNs, which immediately tells us that evolving robots that have CTRNNs, they're able to remember things from the past. That's what recurrent connections give us. Continuous time takes us into the world of calculus. There's 2 places in this course where we're going to do a little bit of calculus. This is the first of the 2 places. Okay, so going all the way back to high school algebra, you can describe the slope of the line, what y equals mx, where m is the slope of the line. It reports a relationship between x, usually on the horizontal axis, and y on the vertical axis. So slope becomes a description of how, when we move horizontally, things change vertically. From here on out, instead of x on the horizontal axis and y on the vertical axis, we're going to put t on the horizontal axis for time and x on the vertical axis for the variable of interest, which is going to be the values of neurons in the CTRNN. So in most neural networks that you're familiar with, the values in those neurons change discretely from time step to time step. We're going to look at neurons inside CTRNNs that vary their values continuously over time. That has an advantage when that neural network is trying to operate a robot, and we'll see that in a few minutes. Okay. So, as you may remember, about 300 years ago, mathematicians started to scratch their head and say, slope is great, but what happens when these differences approach 0? How can I describe the relationship between, in our purposes, t and x, as we make infinitesimal changes in t? As delta t approaches 0, what can we say, if anything, about how x changes, which led to the birth of calculus? Most of you are familiar with, from calculus, with differential equations. We'll get to those in a moment. I want to contrast differential equations with difference equations, which describe a way of describing how things change over time discretely. So if we want to know what the value of x is at the next time step, t plus 1, we can describe it as take the previous value of x and add 1 to it, and that describes a particular change to x over time. So that's a difference equation, discrete changes in the variable of interest over time, like in traditional neural networks. Continuous time recurrent neural networks, we're going to describe the behavior of each neuron in a CTRNN as a differential equation, which mathematically can help us describe or sketch out how that neuron's value changes continuously over time. Yeah? So just a reminder, dx over dt, we're going to be working with that today. Dx over dt, if you were to describe it verbally, means the rate of change of x, the rate of change of the variable's value, the neuron's value. The rate of change of the neuron's value is equal to the rate of change of dt in this simple differential equation here. Some places I'm going to represent it as dx over dt, other places as x prime. Seem vaguely familiar to everybody? So far, so good. I see some nods. Okay, all right. Okay, so let's go back up here. Let's go back and revisit our understanding of how normal neural networks work, discrete time neural networks. If we want to describe the value of neurons inside a neural network, we can write it as follows. X is the value of the neuron. at a certain time. That's going to be the subscript. And the superscript, put in brackets to remind us that this is not an exponent, is the index. So this difference equation here says the value of the first neuron, or the new value of the first neuron, is a function of something to do with its past value, plus other stuff. If we write it out a little more fully here, we can describe how to set the value of the first neuron at the next time step, t plus 1, as some function wrapped around a weighted sum. What is this weighted sum? We take all of the synapses that are arriving at x1. We take the first one, which we're going to call W11, W for weight. So we take the synaptic weight of the first synapse arriving at neuron 1, and we multiply that weight by the value of that synapse's presynaptic neuron. We go backwards along the synapse, backwards along the arrow. We get the value of that neuron at the previous time step, multiply it by its synaptic weight, go to the next synaptic weight, which is W21. This is the weight of neuron 2's influence on neuron 1. We take that weight, multiply it by the value of neuron 2 at the previous time step, and so on. So this is this times this, plus this times this, plus this times this. That's how you update a neural network, described as a difference equation. We take that weighted sum and we push it through an activation function, and that gives us the new value of the neuron. All good? Okay. All right. We are now in the red box here. We are going to start to build up not a difference equation, but a differential equation that describes the rate of change. Remember, that's what the comma here tells us. Y prime tells us we're going to try and describe mathematically how the value of the ith neuron changes over time. We're dropping the t subscript, the time indexing. Okay, I'm going to walk through this and I want you, if you're taking notes and annotating, you see we're going to add terms. So wherever you see some of these terms in the red box, put them at that horizontal location so you leave space for the other things we're going to fill in. We're going to gradually build up this differential equation one term at a time. Okay. Continuous time, CTRNNs have much more neurobiological detail in them than traditional artificial neural networks. Artificial neural networks are very stripped down approximations of how brains actually work. CTRNNs are going to put a fair bit of that biological detail back in. And we'll see in the math which biological features of neurons are captured. Let's look at the very first term. The first term is minus y sub I. So the rate of change of the ith neuron is going to be set equal to its current value times minus 1. Let's draw how this neuron's value changes over time. So we've got t on the horizontal axis here. Oh, the other note is to follow the notation of the paper in which CTRNNs were reported, which is the assigned reading for today. We're going to switch from x representing the neuron's value to y. A little confusing, but doesn't matter too much. Okay. Y sub I. Remember that we're just describing the behavior of one neuron inside a CTRNN. Okay. What does a differential equation with a negative on the right-hand side do? What does it mean?
It's going to be like exponential, but like always decreasing.
Always decreasing. Okay. So the value is always decreasing, possibly. We first have to say decreasing from what? So when we're dealing with differential equations, if we want to understand them, best thing to do is first assign an initial value. So let's just assume for argument's sake that at a given point in time, the ith neuron inside a CTRNN has a value of plus 1. That's its current value. Y sub I at this moment in time is plus 1. How does the value of the ith neuron start to change over time as we march forward in time?
It's going to exponentially decay and kind of just approach zero infinitely?
It's going to exponentially decay, as was mentioned a few times, right? So we plug in +1 on the right-hand side. +1 times -1 is -1. The rate of change is -1, so we start to go down. As we go down, the value of y sub I is now less than +1. Let's say at this moment in time, it's about 0.7. We can plug 0.7 back in the right-hand side to track our intuition for how this differential equation works. Now we have the rate of change of y sub I is equal to -0.7, which means the rate of decrease has decreased, as was mentioned, right? We get an exponential decay. It approaches 0, but never reaches it. Everybody see that? Okay. Let's look at another example. Let's imagine at another moment in time, for whatever reason, the ith neuron inside the CTRNN has a value of -1. Now what happens? The differential equation, again, is describing how this neuron behaves.
It's the same plot, but flipped over the t-axis.
Absolutely, it's flipped, right? So we plug -1 into the right-hand side. -1 times -1 is +1, so we get an increase. The rate of change of the value of the ith neuron is going up, but as it goes up, we now get to something like -0.6. Plug that into the right-hand side, and now the differential equation tells us at this moment in time, the rate of change of this neuron is plus 0.6. It's increasing, but at a decreasing rate, and as was pointed out, it always approaches 0. No matter what value of the neuron it is, as time goes forward, all other things being equal, we're going to add some more mathematical detail to this equation, but not yet. All other things being equal, a neuron's value will always decay back to 0. That is capturing arguably the most important biological detail of neurons, which is I see some of you having your breakfast. It's a good thing because you need your brain today, because your brain has 3% of your body mass but burns 20% of your calories. What detail are we capturing here in the math?
It's like burning energy.
Neurons burn energy. They absolutely do.
Tendency for neurons to return to their cell equilibrium.
The tendency to return to equilibrium, perfectly put. For our purposes, that's it, right? If you're a huge energy hog, you're a neuron in someone's skull, you're doing good work for that person, you don't want to be burning energy all the time if you don't have to. If you're not needed, so to speak, neurons always decay back to equilibrium. They rest as best they can. Remember our example about bipedal locomotion, the muscles in your leg relax? Your body and your brain was designed that when a part of your body or brain is not needed, as best it can, that part should return to 0. It's capturing a very important feature of neurons. Now, a question.
I was just going to say, like, if it always goes to 0 over time, are we going to add in a part that adds in like little restarts into it to allow it to
We'd better,
activate?
or else the CTRNN is not going to do very much of anything, right? Okay, so we're going to add some detail. That's why I say all things being equal, if there's no other influence on the ith neuron, it'll rest. Yeah, good advice for all of us. Okay, generally speaking, neurons are energy hogs. They're also lazy. The moment they're not needed, okay. So let's start to add in a little bit more biological detail. We're now going to add tau sub I, and we're putting it on the left-hand side. Tau sub I is a time constant. We'll talk about it in a moment. You may or may not have seen addition of terms on the left-hand side of an ordinary differential equation. When you were taught ODEs, usually it was just the variable of interest. In our case this morning, y sub I. Usually it's the only variable on the left-hand side. This is just kind of notational laziness. We're putting tau sub I on the left-hand side. You can imagine dividing everything, when the screen comes back on, dividing both terms on the left and the right of the equal sign by tau sub I, and you get y prime sub I equals minus yi divided by tau sub I. Mathematicians are also lazy. If we don't have to write things as a fraction, it's just easier to put tau, in this case, on the left-hand side. Yeah? Okay. So makes it a little bit more work for you this morning. You got to kind of mentally divide both sides by tau sub I. Comes out to the same thing. Okay, so what does this time constant do? This is not a variable, this is a constant, time constant. So when we design a CTRNN, or when an evolutionary algorithm evolves a CTRNN, that the optimizer, either the human or the evolutionary algorithm, is going to set tau sub I for a given variable, for a given neuron. So every neuron inside a CTRNN is going to have its own tau. That's why, that's the subscript I as a reminder. And it's a constant. Over time, the value of y is changing, which is the value of the neuron. The tau for a given neuron does not change over time. It's set. Yeah? Okay. So let's try and build up an intuition for what tau sub I does. Let's go back to our original example of starting off the ith a neuron with a value of +1. At some point, it's got a value of 1. And let's assume that it has a tau sub I of 0.000001. So it's a positive value, but it's very, very close to 0. How does that additional detail, how does that differential equation change the behavior of y sub I compared to when it didn't have a time constant? What happens now?
It's going to get super shrunk and be really steep at the start and then drop off really quick.
It's going to be very steep because we've got 0.001. So if you divide both sides by 0.001, we get on the right-hand side -1 divided by 0.001, which is some very large some very large negative number. So the rate of change of y sub I is now much steeper than it was before. It's going to start to drop much more steeply. And depending on how we simulate this neuron, in some cases it might actually drop below 0 very quickly. If tau is close enough to 0. What happens now? Let's assume it's actually reached -0.6. What does the neuron start doing now? I see you doing some of this. This is possible. A neuron with a time constant close to 0 is a Woody Allen neuron. Let's test your cultural knowledge here. Woody Allen's very neurotic New Yorker. If you ever watch a Woody Allen movie with him in it, any little thing will set him off on some crazy oscillation. He's all over the place. Ultra sensitive. Any little perturbation and a y sub I with a tau near 0, very, very sensitive. You also have neurons in your central and peripheral nervous system that are like Woody Allen. Just takes a little bit and boom, off they go. Any guess why? These kinds of neurons, plus Woody Allen when he's in that state, burns a lot of energy. Better be a good reason for it. Things related to a fight or flight response. So in your visual system, if there's something that looks like a snake down here in the blurry part of your vision, if that suddenly happens, there are some neurons like this that take over very quickly before you even know it. You touch a stove and there's a local increase in heat at a certain rate. The Woody Allen neurons in your spine, there isn't even time to get the signal up to the brain, will take over and you'll pull your hand back from the stove before you've even realized that it's happened. There's very good reasons to have extremely sensitive neurons inside your nervous system. Okay. You can probably imagine where we're going next. Let's again imagine an ith neuron, y sub I, with an initial value of +1. And now let's imagine a very high magnitude value time constant. So tau sub I is now 10 to the 6. Now what happens? How does that neuron behave? with a very high magnitude time constant.
Flatter rate towards zero.
Absolutely, right? So we've got -1 on the right-hand side of our differential equation divided by 10 to the 6. We get a very small rate of change. And it will still asymptotically approach 0, but much, much, much slower. Same neuron, but now with an initial value of -1. These are Eeyore neurons. Again, testing your cultural knowledge. Who's Eeyore, for those who don't know? I see some of you smiling. I'm not that old. Good.
The sad little donkey from Winnie the Pooh.
The sad little donkey from Winnie the Pooh. I was reading about Eeyore to my son last night, exactly. Eeyore is kind of sad, never in a hurry, takes a huge amount of effort to literally push him to do anything. Quite phlegmatic, doesn't move around very much, has huge mass and inertia. Again, not surprisingly, you also have plenty of Eeyore neurons, not so much in your spine, more in your brain. Much more in the front part of your brain. More strong hints for you. What's the value of an Eeyore neuron? Also burns a lot of energy, right? This is very far from 0.
Kind of like slow planning and critical thinking.
Humans, for better or for worse, we live in the past and the future. We can think about the future and slowly plan out what we want to do, take tiny steps in that direction. We can inhibit our behavior and do things very slowly in long sequences if we want. Takes a lot of effort, and this thing is chipping away at our ability to do that, but you can still do it with practice. It requires neurons that have this ability to hold on to something and exhibit very slow rates of change. Yeah? Okay. So as you can see, the time constant is also capturing some important neurophysiological details, which arguably are also going to be important for robots as well. An autonomous vehicle that's driving fast down the road and immediately sees a beach ball roll out into the road behind a parked car, you better hope it's got some Woody Allen neurons and can quickly put together what that beach ball implies about what's going to happen in the next few tenths of a second and not think too long about it, right? Slam on the brakes. We probably want, if we want safe robots, they should also have the equivalent of pulling their hand away from the stove before they've even realized it. We probably also want robots and AI that have Eeyore neurons, that are able to think slowly, inhibit their first thought about what to do or their first action, think through things before actually conducting actions in the real world. Any questions about any of that before we push on? Okay, let's add a little bit more math, which hopefully this term looks more familiar to you. So we're still describing the rate of change of the ith neuron. Let's imagine now that we're dealing with a CTRNN that has uppercase N neurons inside it. We can now see that the rate of change of the ith neuron, how the ith neuron changes is being influenced by all the other neurons in the CTRNN. So let's draw a CTRNN made up of uppercase N equals 5 neurons. Usually when you draw a CTRNN, and we'll see some pictures of it, they're drawn in a ring. It's fully connected. So this neuron is connected to the other 4 neurons, plus itself, a self connection. This neuron is attached to all the other 4 neurons with synapses as well, plus a self connection. I won't bother drawing the rest, but you get the basic idea. So we have a fully connected neural network. Given the fact that it's fully connected, there isn't really a sensor layer and a hidden layer and an output layer, as you've probably seen before. It's a big, tight mass of synapses. Okay. So we are taking the values of all the neurons in the CTRNN, multiplying them by the synaptic weight that connects the jth neuron to the ith neuron and summing it all up. So here's our weighted sum that we've seen before. the values of all the other neurons plus its own current value are going to influence how that neuron changes values moving forward. Everybody see that? Okay, pretty familiar. Some other odd things in a CTRNN. We're going to put the activation function inside this weighted sum. Usually, it's drawn outside this weighted sum. We're putting this particular activation function around the value of y sub j itself. In CTRNNs, there's a particular activation function that tends to be used, which is the hyperbolic tangent function. For our purposes, the only thing you need to know about tan h is that it takes any value of x from minus infinity to plus infinity and squashes it to a value between -1 and +1. So you can think about the value that is leaving yj. Inside y sub j, it might have a value between minus infinity and plus infinity, but when it sends a signal out along the connection that connects it to I, the value that it sends outward is going to get squashed by the activation function. Everybody see that? Okay. So far, so good? Questions? Okay, let's keep going. There is another constant that's introduced in CTRNNs, which is the gain of a neuron. So we have a single subscript here, which is reminding us that this constant, there's a different constant associated with each neuron in a CTRNN. If we have 5 neurons, there are 5 Gs. If there are 5 neurons, there are 5 taus for the constants. If there are 5 neurons, how many Ws are there? 25, right? Okay, so we've got a whole bunch of parameters that describe or alter the way that neurons behave in a CTRNN. We're keeping a count, right? 5, 10, 35. What does the gain do? Imagine a particular neuron. Imagine a particular neuron inside, let's call this the jth neuron here. Imagine the gain of this jth neuron is 0. How does that neuron influence the other neurons? What have we done by setting the gain of the ith neuron to 0?
Made it so it doesn't influence the other neurons?
It doesn't influence them. We've silenced it completely. In effect, we've erased it from the CTRNN. Yeah? What about a jth neuron that has a very large gain, a G sub j of 10 to the 6? What are we doing?
Essentially muting everything else.
Possibly muting everything else. So if we look at the ith neuron now, basically the behavior of I is being mostly influenced by j, assuming that the gains of these other 3 neurons plus the gain of this neuron is much less than 10 to the 6. It's called the gain because we're turning up the volume of the voice of that neuron. How much it influences all other neurons. We can turn up W as well, which it turns up the local influence. It turns up the influence of J on I. If we turn up the gain of J, we turn up the influence of J on all the other neurons, including itself. Why introduce a gain term? As we're going to see in a few minutes, we're going to see an experiment in which the experimenters took all the G's, all the W's, and all the taus and turned them over to an evolutionary algorithm. It allowed the evolutionary algorithm to set all the taus, G's, and W's. Why let evolution, or why let an optimizer play with G?
Some neurons should be more important than others, and maybe you set up a neural network with certain neurons that just shouldn't be used at all.
Maybe they shouldn't be turned. So we're giving an evolutionary algorithm, or making it easier for it to turn off a neuron if it's not needed. In theory, a bunch of mutations could turn off all the outgoing synapses from the jth neuron, but that requires a lot of lucky mutations in a row. If it's ultimately just useful to get rid of this neuron, it can do it with one mutation, or maybe a few mutations that take G sub j close to 0. Alternatively, for whatever reason, maybe the evolutionary algorithm sees an advantage turning up the volume of a given neuron or subset of neurons, and mutations that hit G in the right way would make that happen. Okay. One more detail. We are also going to define one more set of constants, theta sub j. So again, there's a single subscript reminding us that for each of the uppercase N neurons in the CTRNN, each neuron has its own theta. Theta is the bias of the neuron. What does a neuron with a theta of 1 do in general? What is the effect? Vertical translation, right? Whatever the outgoing value of the jth neuron is, remember that all this stuff is being pushed through the tan H function, which squishes the outgoing value from the neuron between -1 and +1. It's vertically translating it up. All other things being equal, it'll tend to emit more positive values. What about a neuron with a theta of -1? Tends to send out more negative numbers, right? So we're sort of biasing, well, not sort of, we are biasing the output of neuron J. The outgoing value of J can still change over time, but it probably hovers around a certain set point. Remember, if we go all the way back to where we started with minus y sub I, we saw that with just minus y sub I, it tends to decay back to 0. If we just had this term and we just had this term and theta was 1, it would tend to decay towards 1. If we had just this term and just this term, that neuron, and theta was -1, that neuron would tend to, quote unquote, settle back towards or rest towards -1. Turns out, again, inside your central and peripheral nervous system, there are also neurons that tend to not decay to 0, but they decay to a certain set point. Like, for example, the neurons responsible for your heart. Keep beating, keep beating, keep beating, keep beating, keep beating. They're sending a positive value to keep those things beating. You don't want the neurons that are controlling your heart to rest to 0 and stop telling the heart cells to all get bigger, all get smaller, all get bigger, all get smaller. Wouldn't be good news for you. There's obvious reasons. You want certain neurons to always keep the lights on. You want them to always be emitting whatever signal they emit. You don't want them to arbitrarily decay back to 0. Okay, so not really a complicated ordinary differential equation, but it is capturing a fair bit of neurophysiological detail that seems to have good evolutionary reasons for being in us, so let's also put it into our robots. Okay. Last bit we're going to add to the ordinary differential equation describing a single neuron is a terribly named variable. I'm not a fan of this notation. Uppercase I sub lowercase I. So we've got I sub I. Not a good choice. The uppercase I reminds us that this is input to our CTRNN. So let's go back to our 5-neuron CTRNN. It's all hooked up internally, but ultimately we want a CTRNN to control a robot. So we need some of these neurons to receive signals from the outside. So we're going to just assign some of these to sensors. So let's assume we have a robot that has 3 sensors on board. We just wire up each of those 3 sensors to some arbitrarily chosen neuron. We just determine these to be the sensor neurons in our CTRNN. Whenever we're describing the rate of change of any one of these neurons, the way in which that neuron changes values is influenced by all this stuff, plus the value coming from outside. The input to the sensor neuron from the sensor. It's this thing. We've got a single subscript here reminding us that there's a single value arriving from a single sensor to that neuron. If one of these neurons does not have a sensor attached to it, its I sub I is equal to 0. There's no external value coming in to the differential equation. So far, so good? Okay. All right. So now we've described the behavior of a single neuron. Now I want you to remember that in our CTRNN, we have uppercase N neurons. So if we have a 5-neuron CTRNN, we can completely describe the behavior of that CTRNN with 5 ordinary differential equations. Each of those 5 differential equations has exactly the same mathematical form, this form, but each of them may have different values of tau, w, g, theta, and possibly I sub I. So far, so good? Okay, we're missing one last detail if we want a CTRNN to control a robot. Output. So it's not described here, but again, we arbitrarily grab some neuron and we attach it to a motor. Whatever the value is here, and remember that thanks to the tanh function, when we take the value out of that neuron, we get a value that's squashed between minus and plus 1. That gets sent to the motor to either spin a wheel backwards, -1, or spin a wheel forwards, +1. -1 might mean flex a joint inward. A value of +1 might mean extend that joint outward. Doesn't matter. That value is interpreted by the motor. For our purposes today, that doesn't matter. Okay, now we've got all the details of a CTRNN. Next, we're going to see how this particular neural network can be useful for a robot. But before I go on, pause. Any questions about any of this? Okay. All right. We're going to look at an experiment today, and the optional reading describes this paper. This experiment is a little more complicated than some of the others we're going to see, so for the undergrads, if you don't pick up all the details here, that's okay. What we're going to look at, or what the investigators wanted to investigate, was a particular aspect of intelligent behavior, which is the acquisition of motor primitives, and then motor sequencing. So what does that mean? What is a motor primitive? A motor primitive is a very short, simple action. Let's assume I'm learning to play the guitar. I'm taught a few motor primitives. Here's how to play a particular note. Here's how to play a different note. Here's to play a different note. Other motor primitives, here's one chord. Here's how you set your fingers on both hands for that chord. Here's how you set your fingers differently for this other chord. I'm taught all of those primitives. Once I start to learn those primitives, I'm then taught motor sequencing. If you want to play this song, you do this motor primitive, then this motor primitive, then this motor primitive. Same thing if you learn a sport. Here's how you kick, here's how you grab, here's how you throw, whatever it is, motor primitives, and then here's how to execute a play. You do this, then this, then this, then this. Remember, I mentioned a few minutes ago that humans are able to think forward in time. We can sequence a bunch of actions and then carry them out. Yeah? Okay, so a tricky thing to get a normal neural network to do this. Turns out that CTRNNs are much more amenable to being taught to learn motor primitives and then exhibit them in different sequences. Okay. This is after a CTRNN has been evolved. This robot has been taught a certain primitive, which is lift the block up and down. It's been taught the motor primitive, move the block left and right. And I think it's going to show, no, okay. So it's got a couple of motor primitives, up and down, left and right. And then you just saw the robot also demonstrate its acquisition of motor sequencing. It's going to do the first primitive 3 times. And it's going to do the second primitive afterwards 3 times. So we're going to teach it simple actions and then teach it how to put all those together. Seems like kind of a simple thing to do. It's tricky to do. I want you to now look at the inset figures, and you'll notice there's some flashing lights called fast and some flashing lights called slow. What we're looking at is an evolved CTRNN in action. What do you think the fast and the slow means?
Which neurons have like a low or high T value?
So here's our Woody Allen neurons here, and here's our Eeyore neurons over here. In this experiment, we're going to see that setting the time constants in the CTRNN make it easier to learn how to do things and then more slowly unroll those things in different sequences over time. Okay, that's the big picture. Let's look in more details how they did this. I've just copied and pasted the math for a CTRNN over here for our purposes. Let's assume that for a given robot, there are 3 different motor primitives we want to teach it. The green one, the blue one, and the red one. If we then want it later, once it's learned to do these, we want it to be able to put them together in different orders over time. We want it to be able to do flexible sequencing, like green, then red, then blue, then blue, then blue, then green, then red, then green, then red, then blue, then blue, then blue. How do we do it? Well, we could try and build a traditional neural network in which some of the neurons in that neural network learn to produce green behavior, another subset of the neurons produce blue behavior, and another set of neurons produce red behavior. Cast your mind back to our discussion about Bratenberg vehicles. Go towards the light. Turn away from the loud sound. Turn towards the dirtier part of the floor. You might remember we talked about subsumption architectures, which was not strictly a neural network, but it was a way to stack different Bratenberg vehicles. And the most urgent vehicle, the one that says, I'm in charge of large sounds, and I hear a growling dog like really, really close on our left-hand side. That Bratenberg vehicle grabs control of the motors and turns the Roomba away from the barking dog, right? Once the sound of the dog gets less, that vehicle lets go of the motors, and one of the other less urgent vehicles says, there's some more dirt on our left-hand side, so let's turn to the left. You have a whole bunch of different vehicles inside the Roomba that are grabbing and letting go of the motors, depending on current circumstances. We can take that basic idea here to do motor primitives. You can think of green, blue, and red as a green Bratenberg vehicle, a blue vehicle, and a red vehicle. And then we've got some additional set of neurons in here that act as gates. These are neurons that make decisions about whether to allow these neuron values to flow all the way to the motors. Or maybe these neurons shut off the connection between the green neurons and the motors, and this gate opens up, allowing these neurons to grab control of the motors. When I say verbally, neurons grab control and release the motors, there are ways in which the values flowing through a CTRNN can influence the motors more or less. I won't go through the math for that, you'll just have to take my word for it. Okay. We can do that, but unfortunately for robots and for you, if you want to survive in this world, it's usually useful to learn hundreds or thousands or arguably millions of motor primitives. It's hard to actually accurately count where a motor primitive starts and ends. You just have to take my word for it. There's lots of little ones that you're capable of all the time. You're not even aware of it. If we similarly want to teach a robot to be behaviorally flexible, we want it to be able to do lots of different things and put lots of different motor primitives together in different sequences, we're going to need more and more neural real estate. We're going to have to keep adding more neurons every time we want to teach a robot to do a different task. You will have only so much room in your skull, so it's also not really wise for Mother Nature to have put the learn guitar circuits over here, and the ear circuits over here, and the drive a car circuits over here. It's interleaved in a non-obvious way in human brains, in mammalian brains. When you learn a new task, you're not grabbing a bunch of neurons that have been sitting idle since the day you were born and then use them to do the new task. You repurpose or you interleave tasks and neurons for very good reasons. Yeah? We talked about bipedal locomotion and the high rate of death in childbirth in humans. You don't want to make human skulls any bigger. We don't want to add neurons and increase the size of the skull. It's very bad news for our species. So Mother Nature wants to try and make most efficient use of the neurons that we have. The investigators in this experiment wanted to see ways in which this could be done. So the investigators, when they taught their little robot here to do three different motor primitives, left, right, up, down, forward, back, they didn't build 3 separate neural components. What they did instead is to evolve the taus, the g's, and the w's, and the thetas, so that they would get some neurons that changed quickly. When those quick neurons grabbed control of the motors, they would cause that behavior to happen. This dashed circle here represents a subset of neurons, a subset of ODEs in the set of all ODEs that describe the CTRNN. This is the same set of fast neurons. These fast neurons can be pushed by other neurons into the blue behavior, or the same neurons can be pushed into the red behavior, and the same neurons can be pushed into the green behavior. Pushed by whom? Pushed by the Eeyore neurons, the slow neurons over here in this set. So the purple represents the values of the slow changing neurons. In this little cartoon here, you can see that collectively these neurons take on some intermediate value, then they go to a high value, then they go to a low value. You can think of these slow neurons over here as the conductor of an orchestra, who's slowly shifting the orchestra from one set of movements to another. When the slow neurons are at intermediate values, let's say they push the fast neurons to exhibit the green values. That's the intermediate. So the robot does green, left, right. Maybe in this cartoon here, twice. As long as the conductor, the slow neurons, hold this intermediate value, the robot will keep exhibiting this motor primitive. So far, so good? Within the slow neurons, they're also influencing one another, and slowly they may shift to higher values. The conductor has now changed how she's holding the baton, and that's now pushing the fast neurons in a different way. So now those fast neurons cause the robot to lift the block up and down repeatedly until the slow neurons drop to a collective or an average low value, which happens to push the neurons into controlling the motors to do this. In theory, they could go back in and keep evolving all of the constants that describe a CTRNN to add a yellow signal, something else. The robot rotates the cube, and these neurons would evolve the abilities for some other value, at some other height of the purple line, to push the fast neurons into yellow. In theory, evolution could keep adding motor primitives to the robot's repertoire without having to increase the number of neurons. Now, whether this is what happens with us is hard to say, but when you learn a new instrument or a new sport, your brain doesn't get bigger, at least not appreciably. You're just evolving, you're learning ways to use your neurons and synapses in different ways. So at a high sort of hand-wavy way, that's what the investigators were trying to do. Question?
You said that again, there's no upper bound on the number of motor primitives for a neural network?
I'm going to turn your statement into a question. Is there an upper bound? Here, it didn't seem so. They never reached it. So the idea, the hope is that there must be an upper bound, but unknown where it is. How many behaviors can you pack into a neural network with a fixed size? Either a biological neural network or a CTRNN. How many motor primitives can you add? and evolve or train or teach that neural network to shift from one motor primitive to another in the way that you want.
So you can optimize in both directions, either adding more neurons or trying to add more primitives.
Exactly. So if we want a robot to do more things reliably, we can either make its brain bigger and add that new capability to the added bit of brain, or we can try and do it in this less intuitive way, which has the advantage of not having to add new neurons. It gets complicated. There's pros and cons to these two approaches. In this early paper from 2008, they just wanted to see if they could do it. Could they teach this robot motor primitives without having to keep adding new bits of brain? Other questions? Okay. All right, so complicated picture. I don't expect you to pick up on all of this. You can see this big ball of spaghetti. You can probably guess what it is. This is a visual representation of the CTRNN. We don't have 5 neurons now. We have, I don't remember how many, a lot. They're grouped into 3 groups. There's the input-output units. These are the sensor and motor neurons. Some of these send motor signals to the robot. The robot does something in the environment, like try and move the block. That movement triggers a sensory repercussion. The robot pushes against the world, and then the world pushes back. Some sensor values come in, and those sensor values re-enter the CTRNN in some subset of these neurons. So these are the sensor and motor neurons. These are hidden neurons. These do not directly influence the sensors and motors. These are manually set by the investigators to be fast neurons. The investigators went in and set the tau time constants for all of these neurons to 5. I don't know how they got the value 5. What's important for our purposes is this value is much less than the time constant for these other neurons here, which are also hidden neurons, which have a tau value set to 70. So evolution does not have control of the taus. In this experiment, the investigators are setting the taus for all of these neurons, and evolution is setting the W's, G's, and thetas. Okay. One last detail here, you see goal up here. Goal is basically just an integer. When the investigators want the robot to shift the block left and right, they would send in an integer of 1. If the robot didn't shake the block left and right, that CTRNN would be deleted from the population of CTRNNs and replaced by randomly modified surviving CTRNNs until eventually they evolve a CTRNN that when a value of 1 goes into the slow neurons, the result is the robot shakes the block left and right. So the goal is do motor primitive 1, which for the robot is this. So far, so good? So delete CTRNNs that when they receive a value of 1, don't do this, and make randomly modified copies of CTRNNs that do a better job of this when they receive a value of 1. In addition, if the value integer coming in here is 2, the robot should do this. If the value coming in here is 3, the robot should do this. So from outside, you can think of the investigator saying, shake the block left and right. Now shake the block up and down. Shake the block up and down again. Shake the block forward and back. We can send in goals, the motor primitives, and we want the robot to faithfully execute those primitives.
As you do this, if you train it for 1 and then you switch to 2 and 3 and train multiple primitives, how do you keep it from forgetting the first one when it switches, or are you constantly using like bi-objective?
That's a great question. So what you're describing is another big problem in the field known as catastrophic forgetting. In this experiment here, we are obviously evolving the robot to try and do more than one thing. So as evolution is evolving populations of CTRNNs, maybe some of those CTRNNs cause the robot to do a better job of shake the block up and down, while simultaneously getting worse and worse at what the CTRNNs used to be able to do, which is get the robot to shake left and right. Yeah. Some of you may have experienced this. If you learn a second or a third language, if you don't keep practicing some of the other languages you know, you start to lose them. It's a very difficult problem for the reason we've been talking about here. Neurons in us and neurons in a CTRNN inside a robot run the risk of catastrophic forgetting. So your question was, how did the investigators set up the fitness function to ensure that it doesn't do this? It's a great question. I'll leave you to read the paper to see the details. But it's a good question. Wasn't easy. Basically, it's don't say 1, 2, 3, and then focus on 3. It's 1, 2, 1, 2, 3, 2, 1, 2. Again, if you're learning an instrument or sport, you're often told by the coach or the instructor to go back and redo some of the things you learned earlier to reinforce that. Don't lose things you've already learned. Basically the same thing here. Okay. All right, last figure we're going to look at. Again, I apologize for the quality of this plot. What you're looking at here is the behavior of one CTRNN. This was the best CTRNN at the end. This CTRNN, when the investigators said left, right, up, down, forward, down, left, right, forward, back, the robot would consistently would be able to follow that sequence. You can see that behavior a little bit if we look at the proprioceptive sensors. So proprioceptive sensors report the angles of the joints in the robot as it's doing its thing. It's a little hard to read here, but in the top here, this is the verbal description of the goal, the integer that was going in, the integer that was going into the slow neurons. So in this experiment, they put an evolved CTRNN back into the robot, and then the investigators, quote unquote, said, reach for the block and then shake it up and down 3 times. Now shake it left and right 3 times. Now go back to the home position. So there are a number of integers that they were putting into this into the CTRNN over time. And you can see the sensor values here plotted over time. You can see 3 bumps, and you'll have to take my word for it. This is the joints changing like this, up and down 3 times. And then when the robot was asked to shake the block left and right 3 times, you can see 3 more bumps, which are the proprioceptive sensors oscillating 3 times as the shoulders, elbows, and wrists shake back and forth 3 times. So we can kind of see the robot doing the right thing. So far, so good. It's exhibiting motor sequencing. I'm going to jump over these plots. Let's focus on the fast neurons down here. These are the Woody Allen neurons. We've got time on the horizontal axis here. So this is the robot shaking up and down, and then shaking left and right. And every row in this panel represents one of the fast neurons. Sorry it's so difficult to see, but on the vertical axis here it says 101 through 160. So the 101st neuron through to the 160th neuron, those 60 neurons are fast neurons. They have a tau of 5. And if you look carefully across these 60 neurons, you'll notice that they're oscillating 3 times. There's a particular pattern as we move from left to right that's repeated 3 times, and then a different pattern that's repeated another 3 times. Let's go back to our orchestra metaphor. Boom, 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 ding, ding, ding. There's 2 different patterns. Each of those 2 patterns is being repeated 3 times, which presumably is what's driving the robot to do what it's supposed to be doing. So far, so good? Okay, last one here, the tiny plot down here in the lower left. This is reporting the 161st through 180th neuron. 20 neurons, which are the Eeyore neurons. These are the slow ones, which during this time period do not exhibit these fast oscillations. They have more or less a constant pattern. This is the conductor holding her baton steady, and the position of that baton is telling the fast ones, bong, 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 which they do. And then she shifts, the Eeyore neurons shift, and they have a little bit, they're kind of following this fast pattern a little bit. So the conductor is kind of wavering her baton a little bit, but generally these slower neurons are changing their values slower. Sorry, I forgot to mention black are negative numbers, white are positive numbers, gray values are values near 0. So we're looking at the change in the sensor values, and then we're looking at what's going on inside the brain of the robot, and we're seeing what we expect to see. All good? Okay, that concludes lecture 8. We've got 10 minutes left, so we'll start in on the minimal cognition experiments. We're dealing with the history of evolutionary robotics. So the minimal cognition experiments are a little old at this point, but they're a classic in the field because they're elegant. They strip away all the complexities of robotics and AI and try and get at the core of the problem, which is we want robots that exhibit different aspects of intelligent behavior. Way back at the beginning of the course, when I asked you to try and define intelligence, most of you gave me answers which were things that you would expect an intelligent agent to do. Defining intelligence in general is notoriously difficult, but describing things that an intelligent agent should probably be able to do, easier. So let's just try and pack more and more of those building blocks of intelligence into simple machines, and let's see how far we can get. Okay. All right, we're going to look at in the minimal cognition experiments, we're going to look at 4 building blocks of intelligence. One of them is known as perceiving affordances. This is something that we do all the time, but you may not be aware that you're doing it. If you look at the 5 objects that you see here, what do they all have in common? It's not a trick question. They're seats. They're chairs, right? They're seats. Seat is a noun. You gave me a noun, right? These objects, I kind of tilted things in my favor. You gave me a noun. When we look at them, we say, they're a seat. If you then try and think about how do you define a seat? If we want to try and teach a robot or an AI to see seats, we'd say, well, it's something that probably has a flat surface and has 4 struts that hold up the flat seat. Oh, wait a second, not all seats have 4 supports. Some have, well, these kinds of supports, and I guess others have this kind of support and this kind of support. And wait a second, I said a flat surface. This doesn't have a flat surface. It starts to get very difficult very soon. If we want to define a chair or a seat, it seems obvious. We describe it geometrically. But when you sit down and actually try and describe a seat geometrically, it's actually hard. That's why I intentionally chose these pictures, right? They're all seat. They all have something in common, but geometrically, they're almost as different as any arbitrarily chosen objects from the real world. Thinking about thinking is misleading. So J.J. Gibson, a psychologist a few decades back, said, that's not how we learn to recognize seats. That's not, whatever it is that we're doing when we look around the world and we're looking for a place to sit, we're not doing just geometric calculations. What we're actually doing is, what Gibson said, is perceiving affordances. So what is an affordance? An affordance is an ad. It's an advertisement projected by objects out in the world. An affordance, an object projects an affordance, which is a quality of an object or an environment that advertises how an individual can perform an action with that object. So, important things, first of all, action. This is a course, among other things, about embodied cognition. So when you look at objects, you're actually mentally simulating things you could do with that object. When you look at these images, if I were to put you in an fMRI machine, there's a particular part of your motor strip, the part of your brain that's responsible for actions or sensation in different parts of your body. The part responsible for thinking about your bum would light up. You're actually thinking about, if I were to sit on that thing, would it support my weight without me falling off? You're thinking about actions you can possibly perform. When I hold up this action, again, if you were in an fMRI, the part of your motor strip responsible for this thing lights up. You think about how or whether you could use this for writing, and on what. Okay, so that's how we make sense of things in the world. When we look around the world, we say look because we're primarily visual creatures, but looking and vision and geometry is a part of what we're doing, but not the only part. We're doing more stuff. We're thinking about our interaction with the objects and the kinds of actions that that object affords. What could we do with that object? All right, let's play the perceiving affordance game. I'm showing you a second set of objects now. What do all these objects have in common?
They're all fuel.
They're all fuel. Okay, another noun. Let's try and do this the affordance way. What do these objects afford you? Energy, heat, warmth, comfort, something like that. It's almost a little abstract at this point. What's the action? The action is kind of your muscles relaxing as you go from out there into here because this room is heated by something that fits in this set. I've kept one of the objects in common. Any given object, like a tree stump, depending on context, can project different affordances. You're all warm and cozy in the room at the moment. We're doing something intellectual that involves speaking, thinking, and writing. So when I hold this up, you probably think about this for writing. If you were near this object and someone was attacking you, you might start to think of it in this way instead. Different objects project different affordances depending on context. Also, very important for robots. We don't want robots that look, or we don't want safe robots that look around their environment and are basically just doing geometric calculations. Presumably, we want robots that when we're looking around the world, the robot is thinking, I could do that with that object, I could do that with that object, I could do that with that object. And maybe more importantly, a robot should be able to think, a human could do that with that object. A human could do that with that object. That human is approaching that object. It looks like that human is perceiving an affordance because they're reaching for the object like this, or they're reaching for the object like this. We want robots that think like us. More specifically, in the case of affordances, we want robots to be able to recognize the same kind of affordances we do. A given robot may not be able to sit on these objects like we do, but if we were to tell a robot, go grab me a seat, it would be able to reason about the affordances for us. So far, so good? Okay, so we got 2 minutes left. We'll just start in on the first minimal cognition experiment. As promised, they're going to strip away a huge amount of detail and they're going to evolve a robot that perceives affordances. Okay, what is this robot? The robot is a square, pretty simple, pretty minimal, and this square down here has 2 rocket thrusters. It's got 2 motor neurons, and those 2 motor neurons can apply force this way, pushing the robot to the right along the bottom of the screen. The second motor neuron sends a value that applies thrust to this rocket that pushes the robot to the left along the bottom of the screen. If both rockets are firing with the same amount of force, the robot stays still. If there's an asymmetry in the 2 forces applied by those 2 motor neurons, it's going to move left or right. So we've got a very simple body. We've got a very simple motor system, 2 motor degrees of freedom. This robot has 1, 2, 3, 4, 5, 6, 7 proximity sensors represented by the gray lines. At every moment in time in the simulation that this minimal agent exists within, there are 7 values coming in, 7 values coming in from the 7 proximity sensors that are being copied into 7 neurons inside a CTRNN. All of the agents we're going to see in the minimal cognition experiments are being controlled by CTRNN. However many neurons this CTRNN has, 7 of those neurons receive values from outside, and another set of neurons inside the same CTRNN are sending values to the rocket thrusters. Everybody remember Space Invaders, the little agent moving left and right along the bottom of the screen? It's like that. in the experiment, the investigators, in the simulation, the investigators are going to drop pairs of objects, pairs of squares. The agent's task is to sweep the underside of this object pair with its proximity sensors and determine the particular affordance afforded by this object pair, which is this object pair passable or not? By passable, I mean, is the separation between the object pair wide enough that when this object pair falls to the ground, the robot could stand between the object pair and the objects would fall on either side of the robot. That's passable. If the object pair is much closer together and the robot determines that if it stood underneath the object pair, it's going to get hit, that object pair is impassable and the robot should move out of the way when the object pair reaches the ground. So they're going to expose these agents to pairs of falling objects, some which are wide enough for the robot to pass through, and others which are not, and the robot should get out of the way. We'll see how well the robot did at evolving an ability to perceive these affordances and do the right thing next time. You have a quiz due tonight, and you're working on assignments 5, 9, or 10. Thanks. See you on Thursday.